In section 6 and 8, we will continue our talk about atomic structure and periodicity. In section 6, we're going to discuss quantum numbers and how they describe the properties of orbitals. We will be able to determine an allowed set of quantum numbers for an electron in an atom. We'll determine the orbital type from the angular momentum quantum number and discuss the significance of each quantum number to the orbital. Okay, so the quantum numbers are going to come from the solved wave equation for hydrogen. That is the only thing we can actually solve the wave equation for, okay? And what we get are many functions that satisfy that wave equation. Now, these solutions give rise to orbitals. Remember the probability density function, the psi squared, the square of the wave function, gave us that probability density map of finding an electron within a given region of space, and we called that the orbital. Now, these orbitals are defined by 3 quantum numbers. Now, there is a fourth, but that fourth one does not come from the wave equation. It actually comes from experiment. We can think of these quantum numbers as essentially seat assignments for electrons. Much like you would have a seat assignment in a stadium, these quantum numbers assign the electron seats. So the first quantum number is the principal quantum number. That is n. This is the one that Bohr determined. Okay? Now, the principal quantum number is going to be an integer with values from 1 to infinity. So 1, 2, 3, 4, and so on. Now what this does is this specifies the energy level of the shell and the distance from the nucleus. So the higher the n, the higher the energy, the farther from the nucleus. We saw that with Bohr's model, where we had concentric circles representing the orbits, where we had n equals 1, n equals 2, n equals 3, and so on. The farther out you got from the nucleus, the higher the energy level, and the bigger the n. The angular momentum quantum number, the second quantum number we're going to talk about, has a designation of L, and it's a scripty L. This number takes integral values from 0 to n minus 1. Okay? From 0 to n minus 1. So, follow through. If n is equal to 1, then the only allowed value for L is 0. Because 0 to n minus 1 or 0 to 1 minus 1 is just 0. If n is equal to 2, then L can be 0 or L can equal 1, n minus 1, 2 minus 1. So there are 2 allowed values for L. And we can do that for all of the different values of n. The angular momentum quantum number determines the shape of the orbitals in the subshell. And we're going to talk about shapes in a few minutes. Okay? Now, shapes in a subshell. The subshell, n gives us this shell, L is the subshell. Okay? Now, we often call these L values by letters derived from spectroscopic studies like the hydrogen atom. If L is equal to 0, we call that an S subshell. If L is equal to 1, we call that a P subshell. L equals 2 is a D, 3 is F, and 4 G. We don't need to go to 4 because that's really, really rare. Okay? Everything we're going to discuss in class we'll cover with S, P, D, and F. The magnetic quantum number, or m sub L, takes integral values that range from negative L to positive L. Okay? Now what this does is this describes the 3D orientation in space of the orbital. Okay? So, n is the shell, L is the subshell, m sub L talks about the 3D orientation in space of the orbital. Okay? Alright. And we're going to see more about that in our discussion of the orbital shape. Okay? Now, here is a table that talks about the first 4 quantum levels of orbitals in hydrogen. So, if n is equal to 1, L can only be 0. If L is equal to 0, then M sub L goes from negative L to positive L. That's just plain old 0. Okay? If n is equal to 2, then L can be 0. And if L is equal to 0, then M sub L is equal to 0. But n can also equal 1. That if L is equal to 1, then negative 1, 0, and positive 1 are also possible M sub L values. And we can go on down the row. Okay? Now here's the key. The sublevel designation that we have talks about the n value and the letter value of L. So we call this the 1s sublevel. It contains one orbital at a shape governed by M sub L, or a 3D orientation governed by M sub L. If n is equal to 2, we'll have the 2s sublevel, again with a 3D orientation, one orbital, 3D orientation covered by M sub L. But if L is equal to 1, this is a 2p sublevel. Okay? Now, there are three orientations in space, the -1, the 0, and the 1. That means that there are three orbitals, one oriented on the -1, one oriented around the 0, and one oriented around the +1. Don't get too hung up on the actual values of these things. These are just telling us 3D orientation in 3 dimensions. 3D orientation, the 3 dimensions, not a number line. Okay? We will see this when we look at the shapes of each of these quantum numbers. The fourth quantum number, which I talked about, that does not come from experiment, is the spin quantum number, and that is M sub s. The spin quantum number has values of either +1/2 or -1/2. Okay, and this specifies the spin of the electrons in an orbital. Okay, do electrons really spin? No, but that's what we call it, is the spin, because we can imagine if electrons are spinning, that they could be spinning in one direction or the other, counterclockwise or clockwise. And this arises from what happens when you pass an electron beam through a high magnetic field. You'll actually split the beam. So here, the incoming electron beam, and you have a north pole and a south pole. The beam comes in and then gets split based upon the spin. Okay? The spin quantum number is really important because it allows us to have 2 electrons in an orbital. So 2 electrons can cohabit an orbital because of opposite spins. Okay? You can think of the spin as also being kind of like constructive versus destructive interference. That when spins are opposite, the interference is constructive, but when the spin is the same, you have destructive interference. In section 7, we're going to talk about recognizing orbitals based on the 3-dimensional shape, recognizing nodes in orbitals, and be able to determine degenerate orbitals. The shape of the orbital is governed by the L value of the quantum number. Okay, and remember, each of these subshells, those subshells contain orbitals, and the orbitals have a specific shape. The S subshell, L equals 0, so that's the S subshell, gives rise to one M sub L value, and that's M sub L is equal to 0. That tells us that we only have one orbital, and it must be spherically symmetrical. So it must have spherical symmetry. So what we have is just a single little sphere. One electron probability map. Okay? Now, if we take a look at our psi squared 1s, what we see is the probability of finding an electron close to the nucleus is high, and it decreases as you go out. Now, what ends up happening is eventually, at n equals 2, L equals 0, the 2s subshell, we get this little drop off here where there's 0 probability of finding an electron. That is what we call a node. Nodes are regions where there is no chance of finding an electron at all. Okay? Now this is actually kind of important because as we see, the farther and farther out we go, the higher the n level, so this is n equals 3, we have more and more nodes. So this is kind of like layers in an everlasting gobstopper that don't touch each other. Okay, there's 0 probability of finding candy between those layers. Or if you know what a Russian stacking doll is, where you pull the doll apart and there's a smaller doll underneath, and you pull that apart and eventually you get down to just the smallest doll. That's the same idea. But this also means that if electrons are traveling from, say, the 2s orbital to the 1s orbital, how do they get there? If there's 0 probability of finding an electron, how does it travel there? Which is kind of creepy if you think about it. It's an instantaneous jump in energy. It goes from one level instantaneously to the next level without traversing a distance. Very, very strange. Okay? So that is part of what comes out of the Heisenberg uncertainty principle. Okay? So let's talk about the next. This is for L is equal to 1. If L is equal to 1, the M sub L values you can have are -1, 0, and 1. From negative L to positive L, 0 inclusive. What this does is this tells us that we've got 3 orbitals, and they're each oriented on a different axis. So, p orbitals are often called dumbbell shapes, because it sort of looks like, well, I guess a dumbbell, if you think about it. But when we do the probability density map, what we get are just 2 regions of electron density, okay? With a node in the center. That's our central node. Okay? Now, each of these orbitals is stacked on each other, so they're not all separate. They're each stacked on each other, so that essentially when you stack them together, you kind of get something that looks like a bumpy sphere. So p orbitals are dumbbell shaped. You get 3 of them, the px, the py, and the pz. Each of those is oriented on one of the 3-dimensional axes, hence the -1, 0, +1. Which is x, y, and z? It doesn't matter. Okay? It doesn't matter whether you think -1 is x, 0 is x, or 1 is x. It doesn't matter to us. Okay? What we want to know is that we get 3 orbitals. 3 orbitals. Okay? Now, each orbital can hold 2 electrons. So you can have a total of 6 orbitals in the L equals 1 subshell. The d orbitals, these start to get a little funkier looking. If L is equal to 2, then M sub L goes with values of -2, -1, 0, 1, and 2. This tells us we've got 1, 2, 3, 4, 5 orbitals. If each can hold 2 electrons, that's a total of 10 electrons in the d subshell. And these guys look kind of like p's, but funkier looking. And again, there's always that origin node. Okay? The dz squared is my favorite because it's kind of got like this circular donut around the center. Then when we hit L equals 3, m sub L's values are -3, -2, -1, 0, 1, 2, and 3. That means we've got 7 orbitals. Each can hold 2 electrons each. That gives us a total of 14 electrons in the F subshell. Now, orbitals can be degenerate, okay? Degeneracy refers to orbitals of the same energy. If you are degenerate, you have the same energy. So, for example, all of the p orbitals within a given subshell for hydrogen are degenerate. That is, they all have the same energy. Now, this is one of the reasons that Bohr's model works for hydrogen, is because all of the orbitals in a given n value have equal energy. But that's only for hydrogen. As soon as we start adding electrons into our orbitals, there starts to be a slight change in the energy of the orbital, and that actually affects how we start adding more electrons. And what we see is we get non-degenerate orbitals. Those p orbitals in the hydrogen subshell all of a sudden become slightly different energies. Okay? Now, the other thing that we can talk about is if electrons or electron configurations where all of the electrons are in their lowest possible energy levels, we call that the ground state. When we had hydrogen, remember we had n equals 1, n equals 2, n equals 3, and so on. I said n equals 1, this is the ground state for hydrogen, because hydrogen's only got 1 electron, it would like to exist in that ground state, the lowest possible energy level, and that is for energy to equal 1, and the principal quantum number, energy level n, equaling 1. In section 8, we're going to talk about the fourth quantum number and something called the Pauli exclusion principle. Alright, the spin quantum number, again, was found through experiment. Now, we can think of the 3 quantum numbers that arise from the wave equation to be like seat assignments, like a section, a row, and a seat. And just like no 2 people can occupy the same seat, no 2 electrons can occupy the same orbital. Okay? If you think about it, this is just like the interference patterns, constructive and destructive interference. Now, the spin quantum number allows 2 electrons to occupy the same orbital if and only if they have opposite spins. Remember interference. Opposite spins means that they are not going to interfere with each other. The Pauli exclusion principle then is stated as no 2 electrons in an atom can have the same set of 4 quantum numbers, n, l, m sub l, and m sub s. They can have n, l, and m sub l being exactly the same, but the m sub s's must be different. They must be opposite spins. Now, the development of the quantum numbers and this Pauli exclusion principle put the final nails in the coffin of the Bohr model. Bohr was right for hydrogen. He provided the framework that we started using to understand the internal workings of the atom, but it was just more complex than he had initially perceived. He couldn't account for those energy differences of electrons occupying the same orbital with different spins. Okay? If 2 electrons were in the same orbital, they had to have different spins. So when you try to apply this to helium, which has only got 2 electrons, those 2 electrons must be in the same orbital, but they must have opposite spins, which means there is an energy difference. In other words, he couldn't account for that mathematically, and he also couldn't account for the energy changes when electrons are added. They become non-degenerate orbitals. So this quantum mechanical model of the atom is what we use as our modern basis for understanding electrons and how they behave and where they're at, because it is the electrons that determine the chemistry.